That's all right. So on the last Thursday and on Tuesday, we talked about chapter 10. We were doing the parametric equations and polar equations. So we're looking at different systems and different ways to graph things. We're going to kind of continue that today, looking at three-dimensional coordinate systems, and then we're going to move that into vectors, which will give us the ability to actually figure out stuff on the three-dimensional plane and use it to actually figure out a force problem at the end. So this just all kind of leads you to that, the three-dimension stuff that you're going to talk, and multivariable stuff that you're going to talk over in Calc 3. So, all right. Three-dimensional coordinate system, basically the exact same as the two-dimensional coordinate system, except we add z. So the main difference is when you're looking at it in terms of on a piece of paper or on the screen right now, we still have a two-dimensional space that we're drawing it in. So the x, the y doesn't go up as in a traditional coordinate plane. The z goes up. The y goes left and right, and the x kind of goes basically towards you and away from you, is how you would look at it. And then the z goes straight up and down. So you can see
X
that.
is depth, right?
Huh?
X is depth is what you would term, well, like the equivalent term to it for like when you would talk about dimensions for like building cabinets
Yeah.
and stuff.
Yeah.
Okay.
Well, I guess it depends on how you look at the shape. Kind of like x and y are kind of like your width and your length, and h is, or z is your height.
Mm-hmm.
Is another way, but yeah, you could technically talk about a depth that's coming out towards you.
Okay.
So, and you can see over in figure 4 over here, that's basically how we'd write a point. So the x and the y is still your first two letters. It's x, y, and then z. So the last coordinate's your z coordinate. Down here, I got a couple examples because when we're looking at a two-dimensional plane, if I just gave you x equals or y equals, they would be a line. Well, now when we're moving to three-dimensional space, that line becomes a plane. So z equals 3 would be a plane through z at the 3 point. So notice that doesn't cross the x and the y because it doesn't have an x and y intercept, but it's every single point of x and y as long as z is 3. So that's where we get that plane there. And the same thing with y equals 5. You have the plane going through 5 on the y-axis. It's straight up and down. So the x and the z can be absolutely anything in that situation. So it's kind of taking that line and moving it basically into 2 dimensions instead of just a single dimension that we would have on a 2-dimensional plane. Couple more quick representations of it. Let's see how equations work with it. So in the first one, if we had x squared plus y squared equals 1, so that's a circle. So in a typical situation, if we were looking at that on an xy plane, that would be a circle around the origin with a radius of 1. So that'd be my unit circle. If we're adding z equals 3 into that, you're going to take that circle and shift it up to the z equals 3 plane. But it's still going to be just a circle. If we eliminated the z equals 3 part, so z could be anything, you would have a cylinder. So again, it's taking that single dimension circle that would be on the xy plane and turning it into a 2-dimensional cylinder, because we don't have any actual volume in the middle of this situation. So same kind of concept we're doing at the line, because z can be absolutely anything in this situation.
So in the figure 9, right, if we're just given x squared plus y squared equals 1, how would we know that it's supposed to be a 3-dimensional shape?
Well, because you have, so we're graphing it in the 3-dimension, the 3D plane. So the z is basically everything. So that's why you'd actually have to go all the way up with it.
Would you also go all the way down into negative space?
Yep, exactly. Yeah, it just didn't actually show it in this graph, but yeah, that's it's gonna continue going up. It's just, again, they couldn't graphically show that. It's one of the problems of showing 3-dimensional space on a 2D plane.
So then they would give us the graph to indicate that it's 3-dimensional, because just giving us the equation wouldn't let us know that, right?
Right. So actually in this one, if you notice right here, where it has that R3, That's
Yeah.
the representation of the three-dimensional space. Because it's basically all real numbers times all real numbers times all real numbers in the plane. So that's where the R3 comes into play. So that's the X, the Y, and the Z. So that right there means a three-dimensional plane. And if you see actually the R2, that's a two-dimensional plane.
Gotcha. Thank you.
You just rarely ever actually see it written that way. All right, now that I have a general idea of what the three-dimensional plane is, if we were in class, I'd have you actually graph a bunch of points out just so you can see how to do it and stuff, but we're not. So we're going to do a couple basic equations and stuff from it. So we're going to look at the distance formula, and then we're going to look at the formula for a sphere. So you can get some general idea on how to actually extrapolate the stuff that we do in a two-dimensional plane to a three-dimensional plane. So the first thing we're going to look at is our distance formula right here. So typically when we're looking at distance in a 2D plane, it's the change in x squared plus the change in y squared, and then we do the square root of it. In essence, you're doing the Pythagorean theorem. If we're looking at it in a three-dimensional space, it's basically the exact same thing, except we're going to add in the z coordinate. And you can see how over here, they gave you the rectangle in three-dimensional space. And we're basically looking at the difference between the x's, the y's, and the z's. And you're doing the distance of that line right there. So in essence, it's an expansion of your Pythagorean theorem and finding distance of a triangle. So it's actually used. So we're looking for the distance from P to Q. So we've got 2 minus 1 squared plus negative 1, I'm almost writing the point, minus 3. Actually, it's minus a negative 3 squared. What happens when you're looking at signs? Don't lose the negative signs. Plus 7 minus 5 squared. You can see how I did it. It was really easy to sit there and go minus and then forget that you have to put the negative 3 in there too. So we've got 1 squared, which is 1. This one's going to be 2 squared, which is 4. And that's going to be 2 squared, which is also 4. So I've got the square root of 9, which in this case is 3. So you can start to see we're not doing anything crazy. That, as I've said, I think I don't know if I've said it in this class, but mathematicians in general are very lazy in the work they're doing. So it's like it's going to continue to work going forward because it makes sense there. We're just going to continue that pattern. There's no point in recreating things and making it more complicated than it has to be. And the nice thing is when we create things, they always seem to work. So we can expand it out later on. And that's what they basically just did there. The distance formula didn't really change. And actually, when we looked at, like same thing with arc length, when we were looking at it with parametric and polar, they were just a continuation of the arc length that we were finding with the regular equations. So we didn't really change anything in those processes. So, any questions with finding the distance? Let's look at the equations for a sphere. I'm going to see a very similar concept between the equations for a sphere. If you remember the equation for a circle, it was the unit circle is just x squared plus y squared equals 1. But if we're going to expand that and move it, the general form was x minus h squared plus y minus k squared equals the radius squared. Again, we're just going to add in the z coordinate. So it's going to be z minus l squared. So, and again, if it's situated at the origin, you can just eliminate the h, k, and l because those are all zeros. So you get the x squared plus y squared plus z squared equals r squared. All right. So we're going to look at this equation, and we're going to find the equation of the sphere, finding its center and its radius. You should have done something very similar in pre-calc when you were doing the circle, or the hyperbolas and the parabolas and the circles, or the ellipse and the ellipses. You were actually looking at the equation and taking in general form equation like this and changing it into the equation that gives us the information. We're going to do something very similar in this situation. So the first thing I'm going to do is I'm going to put all the x's together, all the y's together, and all the z's together. So I've got x squared plus 4x. Then I've got plus y squared minus 6y. That's z squared plus 2z. Plus 6. Actually, and I'm going to move the 6 over while I do this instead of doing it the next step. So now what I've got to do is I've got to come up with the perfect square for each one of these. So for the x, for the y, and for the z. So quick way to do that, you just say take the middle number, divide it by 2, and square it. So 4 divided by 2 is 2. 2 squared is 4. So x squared plus 4x plus 4. And then remember, I have to add 4 to the other side as well. And then I have negative 6 divided by 2 is negative 3 times, or squared is 9. So minus 6 squared plus 9. And I got to add 9 to the other side. And then the z is plus 1. So I got to add 1 to the other side. So this becomes x plus 2, y minus 3, and z plus 1 equals 8. So we've got our center is at -2, 3, -1. And my radius is the square root of 8. If you want to reduce it, is 2 square root of 2. So you can really see how like everything's basically just expanded from what we typically would do. And Desmos does not do a good job of graphing 3 dimensions, unfortunately. Although if you have a TI-89 calculator, I think, and I don't think many people have the TI-92 anymore, but the TI-89 calculator does actually graph 3 dimensions, and so does the Inspire. Will graph in 3 dimensions as well. So I remember buying the TI-92 calculator to graph the mountains and stuff in Calc 3. All right, any questions with the equation of a sphere before we go into the heart of tonight's lesson? All right. So before we actually do the actual lesson, I want to show you a use case. We're not going to actually do this, but I want to actually show you the use case, and then actually we'll go through and actually do all the work from it at the end. So we're going to start looking at vectors. And we're going to look at vectors in 2-dimensional space and 3-dimensional space. So because the rules are exactly the same, again, we just are adding an extra thing. So this is a very good example of where you would actually use vectors to do some actual in this case, engineering. So this is a load bearing problem. So you got a 100-pound weight, hangs from two wires, and we're going to find the tension forces in these two wires. So we need to find the magnitudes, and we're going to actually find the vectors for these two wires that are holding up that 100-pound weight. So this is where we actually really start to use all the vectors and stuff that we're going to talk about, because we need the actual math and the algebra to be able to do those calculations. So that's what we're going to look at. All right. So a vector. So we've got these two vectors right here. So a vector is a ray. If you remember from your geometry classes, it has a starting point. It typically does have an endpoint as well, but it can go on forever as a ray. It would be an infinite vector. Most vectors have a magnitude, so it's a length. So it has a starting point and ending point, even though it has an arrow at the end. The arrow actually doesn't represent that it keeps going. The arrow represents the direction that it's going, because the ray has that direction plus the magnitude. If we're looking at this one right here, you've got two vectors. You've got vector A, B, and vector B, C. And we're doing, they're putting together. So you also have vector AC, which is the combination of those two vectors. And that's where the math and stuff starts coming in. It's how are we going to take these vectors and put them together to find other pieces of information. So we've got two different pieces. Actually, I'm going to move this one over. Actually, I'll delete that. Put it on the other one. So the first thing we're going to look at is vector addition. So vector addition is doing exactly what I just showed you in that other problem. It's taking two vectors and putting them together to find a new vector that shows me from the beginning point to the end point. So this is, they showed as the triangle law or the parallelogram law. In essence, the exact same thing. It's just a matter of, because remember, addition is commutative. We can go either direction with it. Same concept here. You got u plus v. We're starting here and going up to the v, or the same thing over here. We have v plus u. It'd be no different in that respect. So you can take two vectors and add them. And
So why is the parallelogram law significant then? If it's the same thing, is there any advantage to using one versus the other?
no, they're the exact same thing. They're literally the exact same thing. It's the law is just saying that you can actually add them together. And honestly, I can't tell you why they have the second one, except the fact that it's commutative. We're going to actually do the calculations in a little bit too, and we'd actually start looking at the component pieces of it. Now, you can't, so we're going to start looking at the calculations a little bit once we start looking at the components. We're going to look at addition and subtraction. Multiplication stuff is done differently. So we have right here u plus v, and we can just put those two vectors together, and we're going to see it very simply done. However, u times v is completely different. So don't look at all the function, all the actual arithmetic features will not work when we're doing these calculations. So addition does work, and because of what I'm going to show you next, subtraction does work. The second thing I can do with vectors is I can do scalar multiplication. I can basically multiply them by any constant. So my original vector was here, that's v. If I had 2v, it'd be twice as long. So I'm basically multiplying the magnitude of it. I'm not changing the direction of the vector, I'm just changing how long it is. Same thing with 1/2. And this is how we could do the subtraction side. I can multiply things by negative. So I have negative v. It's going to be, and notice it's the exact same length or magnitude, but it is the opposite direction. Kind of like what we were doing with the polar coordinates on Tuesday, where the negative radius would just take, it'd be the same direction, but the opposite direction. Be the same length, same angle, but the opposite direction. Same thing with the v's or the vectors. We have the negative v, negative 1.5 v would be longer, also in the exact opposite direction of the other vector. So these two rules, the addition rule and being able to multiply by a constant, allows us to do both addition and subtraction of our vectors. And if you happen to multiply by 0, it basically just gives you a 0 vector. So typically our values are greater than 0. Any questions with addition, subtraction, or addition and then the scalar multiplication? All right, then let's actually use it. Okay, so when we're looking at a vector, we need certain pieces of information about it to be able to do some calculations. So the first thing, actually double this one too. I made these slides and then you realize you want to do something different with it. So we have our vectors right here. Every one of these vectors can be represented by a specific, by the same vector. So we can represent all these as 3, 2. Because all these vectors go in the exact same direction. All these vectors have the exact same magnitude. The only difference is where is it starting and where is it ending. So by representing it as 3, 2, that's known as my position vector. The only difference between a position vector and a regular vector is the position vector starts off at 0, my origin. So notice these are in the 2-dimensional plane. The 3-dimensional plane is exactly the same thing. It just has a third dimension to it. So it'd be A1, A2, and A3. Okay. To find the position vector, all I'm going to do is subtract the endpoint and the starting point. So x2 minus x1, y2 minus y1, z2 minus z1. And that will give me the length or the magnitude of that vector, because it's going to tell me the endpoint of where it's ending, and then my beginning point will then be at 0. So we're finding the change in your x, the change in your y, and the change in your z. And at that point, then we can plug it into the distance formula to find the exact length of it, because it's going in, it's not a straight line at that point.
I'm sorry, so how do we find the position vector? By using formula for A?
Yeah, so basically your position vectors, you're just subtracting the endpoints. So as you can see, like in this one over here, we're starting off at x, y, z, and then it's going over to some other point. And notice that some other point is just x, y, and z adding something to it. So we're adding A1 here, A2 here, and A3 here, right? Does that make sense, Stephen? Or that's not, it doesn't make sense. Do you see it, I should say?
I do see it.
Okay. So the only difference between that vector and my position vector is I'm eliminating the x, y, and z where I'm starting, because I'm starting at 0.
Oh, I see. So by eliminating the X, the Y, and the Z, you're only left with A1, A2, and A3.
Right. Which is, so it's basically, it's going to be the exact same vector. I'm just moving it to the origin to make my calculations a little bit easier.
So I guess the question I have then is if we're given a set of points B and a set of points A, just randomly, and we subtract B from A, that won't always result in a position vector, will it?
Yes. That's literally my next problem I'm going to do.
Sorry.
No, that's fine. You led right into it. So here's the problem. So we've got our vector. Our initial point is 2, -3, 4. And my terminal point is -2, 1, 1, and that's B. So we're going to take and label my points. So that's X1, Y1, Z1, X2, Y2, Z2. And we're going to subtract. So we've got -2 minus 2. We've got 1 minus -3. And we've got 1 minus 4. So I've got -4, 4, and -3. And that is my position vector. So we're just looking for the change. So if we've shifted it over, that's where the terminal point would be, with my initial point being at 0. Or my origin. That makes sense?
Oh, so the point A is where the vector ends if it starts from 0.
Yeah, so this is this is my position vector. So that's the one. So this is starting at the origin to that point. So where my original vector started at A and went to B. So that's the little a is what they were using, the vector A. Let's actually do another one. So if I had, starts off at 5, -2, and goes to 7. So this vector is in 2-dimensional space. It's just A is 5 and -2, and B is 7 and 3. So if we look at a quick graph of it. So we've got my initial point is at 5, -2. And then 7 and 3. So that is my vector. So we're starting at A and we're going to B. And we're going in that direction. I want to take the same point and start it here. So I want to take the same vector and start it at the middle. So we're going to do the same thing. We're going to do, so it'll be 7 minus 5, and then 3 minus -2. So I've got 2 and 5. So I'm going to go over 2 and up 5. So these two vectors are the exact same. One just starts at the origin. So one's the position vector.
So we're just creating the origin vector to make the parallel lines between the two to go from 2D space to 3D space for this, right? Is that what
We're doing them to make them parallel lines. Yes, they're parallel vectors because we can move them around. They
Yeah.
go in the same direction. So that's the case. It doesn't matter two-dimensional space, three-dimensional space. The rules stay the same. We're not making it go into two-dimensional space or making it go to three-dimensional space. This one just happens to be a 2D one, where this one was a 3D one.
Okay, you just
The reason we want to move it to the position vector is because all the rules and everything else still apply. So like I can still find my magnitude, I can still find the endpoints. We can actually do some other calculations and stuff with it without having to worry about where it was starting. It just eliminates information that's not necessarily needed to do a lot of the other calculations.
So this is very reminiscent of slope. So, so if I'm looking at a three-dimensional shape, does a three-dimensional shape have a slope?
Yeah, it's still a line. It is still definitely. It's still a line. So yes, and even in three-dimensional space, you can still have slope. Calculation's a little harder because it's not just y over x. But you do still have slope. Any kind of shape that you're gonna have slope for. That's one of the big things when you move into Calc 3 is we're looking at multivariable. You're going to look at three-dimensional shapes. You're still going to be finding slope. You're still going to be finding derivatives. You're still going to be finding integration. So it's just with three-dimensional space instead of two-dimensional space. Does that answer your question, Stephen?
Yes.
Okay. All right, so we found the ability to move it. So we found the ability to get the position vector. The next thing we want to look at is how to find the magnitude of it. So my magnitude, if you look here, it's the distance formula. So when we're looking for the magnitude or length, we're just doing the distance formula for it. And you represent it with the 2 bars, kind of looks like absolute value. Kind of how that's how we represent the magnitude or length. You can actually see it that way or with the double bars, depending on where it is. So either one of those will still represent the magnitude or length of that vector. Same thing here, 2 dimensions. There's just the 2 of them, 3 dimensions, this is 3 of them. Notice, however, that these are now just A1, A2, and A3, and they are not the X2 minus X1, Y2 minus Y1, and Z2 minus Z1, because these are dealing with just position vectors. Once we get it down to the position vector, my other points were all zeros. So I don't need to worry about using the more complex distance formula. I just need to use the A1, the A2, and the A3, which is the points they gave you in there. Also notice, so if you can see to the terminology. So notice how they say this is my vector, it's represented by this point to this point. Notice that when I write my position vector, I'm writing them with the almost like the greater than less than symbols. The slanted or the pointed brackets. So that's the representation of a position vector. So when you see that, you know it's A1, A2, and A3, or A1, A2 if it's two dimensionals. So that symbol actually has meaning when you're doing it. So same thing here. I've got A is that one and B is that one. Those are two different vectors. That's not a starting point and ending point. Does everybody see that? Okay. So that's my magnitude and length. When we're doing addition and subtraction, all we're going to be doing is adding or subtracting the terms together. So A plus B is just each term, A1 plus B1, A2 plus B2. And then if there was a third one to be A2, A3 plus B3. Same thing with subtraction. We're just subtracting them. If I'm going to multiply them by a constant, so that's that scalar multiplication, I'm going to do that C. So I'm just going to multiply every single term by that constant. And then they have the three-dimensional ones down here, same thing. Now let's use it. All right. Any questions on these setups there? Before we actually go do them? Okay, so we have two vectors here. I got vector A and vector B. The first thing they want is the magnitude of vector A. So that's 4 squared plus 0 squared plus 3 squared. So you've got 16 plus 9. So my magnitude of vector A is 5. And this one, I'm just doing the vector or magnitude of vector A, so I'm not using the B at all in that situation. If we wanted, they don't have it there, but if we want to, we want to find the magnitude of vector B, we would do the same thing. We're going to use just the B. So we do -2 squared plus 1 squared plus 5 squared. So we got 4, 5, so equals 30, which is just the square root of 30. So that'd be the magnitude of vector B. Can't simplify that one. Everybody see the connection between this and the distance formula? The nice thing, like I said, once we have the position vector, we don't have to worry about those extra terms. All right, next piece. They want us to do A plus B. So this is adding those two vectors together. So we're going to do 4 minus or plus -2. So 4 minus 2, 0 plus 1. And then 3 plus 5. So that is 2, 1, 8. And when we're looking at this, so if you, in essence, what we're doing is this. Let me what color it was. All right. So we've got vector A, and we're adding vector B to it. So my new position vector is A plus B. So it's still going back to the origin. That's why it's still in the position vector. So you can see how they showed it out. So that would be the A1 plus the B1. So that's the X value. The A2 plus the B2, that's the Y value. And then this example we were doing was in 3 dimensions. The picture is obviously in 2 dimensions. So we would have the third one as well. But the concept stays the same. So it's still a position vector because it's still going back to that origin. Subtraction, I do the exact same thing, except I subtract. So A minus B. It's going to be 4 minus a negative 2, 0 minus the 1, and 3 minus the 5. So we have 6, negative 1, and negative 2. So, and that's no different than saying it's A plus the negative 1 times B. So that's why we can do the subtraction and addition same because of the scalar multiplication. All right, next ones we got 3B and then we got 2A plus 5B. So those, let's do a little more calculations on. So we've got 3B. So this is just 3 times negative 2, 1, and 5. So you're going to treat this almost like you're just doing distribution. We're going to multiply everything inside by the 3. So this becomes negative 6, 3, and 15. So you're taking each one and multiplying them by the 3. Two A plus 5B. Same rules apply that we were looking at if this was just a normal problem. We multiply the A by 2. We multiply the B by 5, and then we're going to add them together after we do the multiplication. So you've got 2 times 4, 0, and 3, plus the 5 times negative 2, 1, and 5. So we've got 8, 0, 6, negative 10, 5, 25. And then we add them together. So we'll have negative 2, 5, and 31. And then that would be the final one. So the order of operations still kind of applies to this, do the multiplication before we do the addition. Any questions with these? All right, look at some properties. So A, B, and C are just vectors, and then the C and the D there are scalars. So commutative property still works, associative property still works. Adding 0 is still in A, just to the identity. A plus negative A is still going to equal 0. going to cancel each other out. Multiplying by a scalar, just distribute to the two pieces. Same thing here. If I had the two scalars and was adding them, I could do the addition of the other one, but okay, same basic concept, just distributing the a through in that case, or the vector through. Multiplication, again, the order doesn't make much difference in the multiplication, and if we multiply by 1, you're still going to get the same vector. So none of these are out of the line. Notice, however, nowhere in here does it have multiplication of vectors. We're going to talk about that next week. How to actually multiply the vectors. All right. So we're now going to look at another way to write the vector. So we've seen the vectors written as a position vector with the, I'm going to call them pointy brackets. I can't think of the actual name off the top of my head for those. There's probably an actual name. And now we're going to look at the I, J, and K way to write it. So I, J, and K are the standard basis vectors. Okay. If you look at it, it's just, so I is in essence your x-axis, J is your y, and K is your z. It's the one there, and the K there. So these are giving you those directions. If we look at our position vector, A1, A2, and A3, and combine them with these, A1 is that part right there. And if I put the zeros there, and I split it up, so that's plus 0, A2, 0, plus 0, 0, A3. So notice I'm basically just putting zeros. So if I added these together, I'm going to get this initial part right here. So that's nothing different. Now, if I assume A1 was a scalar and I multiply it by 1, 0, 0, it's going to give me the exact same thing again. Same thing with A2 and the same thing with A3. And then we replace these with I, J, and K. All right, so the question is, does everybody see how I went from that to that? Silence is yeah.
I get it.
Okay, so that big silence is yes, because nobody wants to turn on the mic and say, yes, I got it, which is fine. So it's, again, there's not a difference in these. It's just two different ways to write it. So we can see this one. I can express this in terms of I, J, and K now. So I've got the 1, the -2, and the 6. So it's 1i minus 2j plus 6k. And 2 dimensions is just I and J, obviously, not the K version. All right. We're going to do the exact same thing we just did in example 4, but we're going to use the new method, or the new standard writing. So we've got A is I plus 2j minus 3k, and B is 4i plus 7k. And we want to express 2a plus 3b. The rules don't change. I'm going to multiply 2 times the x. So it's 2 times I plus 2j minus 3k plus 3 times 4i plus 7k. So I've got 2i plus 4j minus 6k plus 12i plus 21k. And now I'm going to put the like ones together. So I'm putting the i's together, the j's together, the k's together. The trick though is you do want to keep them in order of I, j, and k. Don't mix them up. So we got 14i. There's no other j, so 4j. And then plus 15k. So these are just two different ways to write it. Two different, since they're writing it two different ways, the process steps are the same, just looks different. All right. Last part of vectors we're going to look at, or this part thing at least. Unit vector. So when you think of a unit circle, my radius is 1. A unit vector is a vector whose length is 1. So a unit vector is not the same as a position vector, because the position vector is taking that vector and moving it to the origin, but the length, the magnitude is still the same. A unit vector is going to tell me the direction. It's going to be the same direction as a vector that I have, but its length is going to be 1. So to do that, we take the distance, the magnitude of my original vector, and we're just going dividing them all by that. So it's 1 over the actual magnitude times the vector. So to find my unit vector, the first thing I have to find is my actual magnitude of the original vector. So the magnitude of 2i minus j minus 2k is 2 squared minus, or plus, negative 1 squared plus negative 2 squared. So we got 4, 5, plus 4 is 9, so the square root of 9. So my magnitude is 3. Now we're going to take my original vector and multiply it by 1/3 or divide it by 3, depending on how you want to look at it. So I have the 1/3 times 2i minus j minus 2k. So my unit vector is 2/3 I minus 1/3 j minus 2/3 k. So that's my unit vector. Any questions finding the unit vector? All right. Now I remember the problem I showed you at the beginning of class. Now, or beginning of the section. Now we're going to do it. All right. So vectors are used a ton in physics, a ton in engineering. This one we're looking at, you can use it to do velocity, acceleration. We're going to look at this one in terms of forces. So the first thing I want to do is I want to figure out what T1 and T2 are. So I'm going to write T1, and I need the vertical representation of it and the horizontal representation of it. So I need something with I, and then my J. So this is in 2 dimensions. And the same thing with T2. Okay, so let's look at this in terms of an actual triangle. So here's my triangle. So we've got some right triangles here. So that's my right triangle. So this right there that's 50. So I'm looking for my horizontal distance right here. So if I'm looking for this value here, that would be adjacent over the hypotenuse. So I'm going to use cosine for that one. So cosine of 50. Now, which direction is this one going? If we were looking at this on terms of the coordinate plane, because direction is going to matter in this situation. Is it going left or right? Is it going to the positive side or the negative side?
It looks negative to me.
Yes, it is going to the negative side. So we're going to make this cosine or negative cosine of 50. I. I'm missing something. Now, I have to, so if I looked at this, we have cosine of 50 equals the x over T1, right? That's how that would be set up. So that's T1 times cosine of 50 equals the x. And we're going in the negative direction. So I got to multiply this by T1, the magnitude of T1. Same thing on the other side. So now I'm looking at the upward value of the y. So that's going to be sine of 50 is y over T1. So same concept. It's going to be T1 times sine of 50. Now this y is going up, so it's going to be the positive. So I've got the magnitude of T1 times sine of 50. And then that's J. So this one is going to be my T1 equation, or T1 vector. My T2 vector, if we're looking at the other side of this triangle, is going to be the same basic setup, T2. We're still looking at this one. The difference is this one we're going to the right, so we're on the positive side. So it's going to be cosine of 32, and it's going to be the positive version of it. And then plus the magnitude of T2, and then sine of 32 to J. Does everybody see where those two equations came from?
So this is where the parallelogram came into play.
Because since since if we move them to the origin, we don't have to worry about all that extra stuff. All right. I'm just rewriting it on the next screen because we need to use it to do some other stuff now. All right, so the next thing we have, so the problem states that the 100-pound weight is hanging from the two wires. So those two wires, the tensions are counterbalancing that weight. So I know based on that I have T1 plus T2 equals the weight. Now, this weight's going in the negative direction, right? So it's going to be negative W. And I know my weight is 100 J. So if we look at it, so my weight was negative 100 J because it's going down. So that's how I got the negative weight equals 100 J. That part make sense? All right. So I can now take this, we're going to eliminate the W, we're just going to deal with the 100J because that's what I'm worried about. And I'm going to put them together. So I've got negative the magnitude of T1 cosine 50 I plus magnitude of T1 sine 50J plus magnitude of T2 cosine 32I plus magnitude of T2 sine 32J equals 100J. So if we take each piece, so I've got negative the magnitude of T1 cosine of 50I plus magnitude of T2 cosine of 32I, that has to equal 0 I, because there's no I in the other part. And then I have T1 sine 50 J plus T2 sine 32J has to equal 100J. All right, is everybody following along? Kinda.
I'm picking it up. It's just you're just adding more steps to the simple process. It's just more steps to it, right? It's really what happened.
Basically. Is it because we're looking because the goal is the first thing we want to find is my magnitudes. So we're trying to find the magnitude of T1 and the magnitude of T2. So since I don't know those, like I can't just use the formula that we had before to find magnitude. I can't just do the square root of it because I don't know the pieces of it. So to find the magnitude, I've got to actually solve for with the 100J because that's what's basically pulling on this. And it's counterbalancing. So the sum of these two vectors basically counterbalances this vector. So that's where they could basically come out to be something that's going to cancel each other out. So if I was to subtract 100J, it's a 0.
This is just forced mathematics, right? I'm making sure because I've taken physics and stuff, so I know that. And they word it differently, so they give you the equation stuff, but it looks like we're creating the equations to do what they already like what I learned in physics.
Yes, that's the wonderful thing about physics. They come up with the equations to do them, so they already have them because they've already done all the mathematics beforehand. This, I'm actually basically showing you how to do it mathematically before we have the equations. This is why physics drives me nuts because they already have all the formulas. So it's like, oh, just do it this way. I'm like, well, where'd you get the formula? This is math. So yes, in essence, that's what we're doing. All right, so we've got two equations. I can now do systems of equations. So I don't feel like rewriting this again. I'm just going to copy it. All right, so we've got those two equations. I'm going to take this one. And I'm going to solve it for T2. So I can say the magnitude of T2 equals T1, the magnitude of T1 cosine 50i divided by cosine 32i. So I took that first equation and solved it for the magnitude of T2. Because now I can take my second equation and substitute that in. Plus the magnitude of T1 cosine I divided by cosine I times sine 32j equals 100. Oh, I didn't even need the i's and the j's at this point. I forgot. Because I solved up for those, so I can actually cancel all the i's and the j's out. So we don't have to worry about this. All right, so I have now the magnitude of Ti, or T1, and then I have sine of 50 plus cosine of 50 sine of 32 over cosine of 32 equals 100. So I can take and do 100 divided by sine of 50 plus cosine of 50 tangent of 32 and get my answer. And we're going to use decimals. So we're going to type that in. So we have 100 divided by, make sure we're in degrees because we're using degrees for this. Sine 50 plus cosine 50 . And 50. 50 . 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. So that answer is 85.64. And then the magnitude of T2 we already had was the magnitude of T1 cosine 50 over cosine of 32. So we now know that that was 85.64 cosine 50 over cosine 32. So we can now plug that into Desmos. So I'm going to actually use the answer. Cosine 50, cosine 32. And that gives you approximately 64.91. All right, so we've got our two magnitudes. All right. So we've got our magnitudes of the T1 and T2. So now once we get the magnitudes of them, we can figure out the tension vectors. Because we had the original equations was written out, and now we know the two magnitudes. So T1 is going to equal 85.64 times cosine of 50 I plus 85.64 sine 50J, which if we do that out, comes out to be, oh, sorry, I forgot the negative sign there. Negative 55.05 I plus 65.60 J. So that's T1. And then T2, same process. So 64.91 cosine 32I plus 64.91 sine of 32J. So we get 55.05 I plus 34.40 J. So that's T2. So now we have our magnitude and we have our tension vectors. Now the engineers and the physicists can go use those to do other things. If we look at it, and this is where your engineering classes come into play and your physics classes come into play, because if we basically just replace these with like an arbitrary numbers, or like actually not arbitrary variables, we could easily come up with a formula for it that would allow you to do this for anyone. And I guarantee that's what the physics teachers give you. Is here's the formula to figure it out. So we just went through and did all the math for it. All right. Any questions with those? All right. So next week, we're going to do the dot product and the cross product. I'm going to multiply my vectors to come up with the more things there. And then that's it. So we got 2 more classes next week, and then you got your review and the test for chapter 10 and 12, and then the review and the final. So we got 3 weeks left of class, almost there. Any questions on anything we've done so far or I've done? If not, you're free to go, and I will see you on Tuesday. If you do have questions, you're more than welcome to stick around and ask.
Thank you, Professor.
Yeah,
Welcome.
thanks, Professor.
Thank you very much, Tony. Appreciate it.
You're welcome.
I'll write this up, send it on to you probably next week, and then we'll forward it on if there's any questions or problems or anything.
Not a
Okay.
problem.
All right. Have a good evening. And if